Hi everyone, my name is Miriam and today I will share with you part of the research study that was conducted at the University of Wollongong about a mixture of waste materials that can be used as a construction fill in transportation infrastructure sublayers, and more specifically I'll be presenting about the strength and deformation properties of coal wash mixed with rubber crumbs. This study was conducted at the University of Wollongong and was supervised by Professor Budima Indraratna, Professor Cholachat Rujikiatkamjorn, and Dr. Anna Heitor, and it was supported by many industry partners. I will begin the presentation with an expressive picture showing a mountain of more than 5 million rubber tires that caught fire in Kuwait in 2012. Such an incident can not only pollute the air with hazardous material and impose health problems to surrounding communities, it can also contaminate the soil beneath it. Another picture on the right shows a mountain of another waste material, which is coal wash. This waste is covering large areas of usable land that can be employed for more eco-friendly purposes. And finally, the view we see on the lower right is not much better than the other two pictures. It shows the damage left behind by natural quarries needed to provide the construction industry with needed aggregates. Now the question is, how are these three pictures connected together? Before we move to that question, let me share with you some numbers. Coal wash is a byproduct of the well-established coal mining industry worldwide. Approximately 20% of the total coal mined in Australia is disposed of as coal wash in landfills. In New South Wales alone, more than 2.9 million tons of coal wash were produced in 2015, out of which only 4.17% were recycled as an engineering material. The remaining tons of coal wash, which means more than 95% of coal wash, was placed in designated areas. It is worth mentioning that it costs approximately $14 to dispose 1 ton of coal wash in these areas. This is equivalent to millions of dollars each year. Now, if you move to waste rubber tires, the numbers are not less alarming. In Australia alone, 56 million equivalent passenger unit of waste rubber tires are generated each year, and only 10% are recycled. While the US generated 287 million waste rubber tires in 2017, out of which only 7.9% were used in engineering projects. Having said all that, we ask the question, what can we do about that? What can we do about these numbers? This brings us to the research objective. Why not use a mixture of coal wash and rubber crumbs as an engineering fill, such as the capping layer in railways? Rubber crumbs are mainly added to the mixture to reduce the breakage of coal wash, which is weaker than traditional quarried materials. To this end, a comprehensive experimental plan was conducted to evaluate the behavior of the mixture with 4 rubber contents. Such a study can significantly impact the industrial as well as the environmental aspects of many construction activities. In brief, the study contains 3 main parts: compaction. So we need to study the compaction characteristics of the mixture, and knowing that rubber crumbs are energy absorbing and compressible, we needed to study the compaction characteristics under the standard Proctor energy levels and the higher energy levels to account or to compensate for the energy that is absorbed by rubber crumbs during compaction and to achieve an efficient compaction. Then we studied the mixture under static and cyclic loading conditions and evaluated the deformation, strength, degradation, and energy absorption properties, as well as other important dynamic properties. In this presentation, we will only cover the static triaxial tests, but if you wish to know more about the other parts of the research plan, I will share with you a list of published work at the end of the presentation. As mentioned before, we used 4 mixtures of rubber crumbs with 0, 5, 10, and 15% added rubber. These numbers were based on a previous study that was conducted on rubber crumbs, coal wash, and steel furnace slag. As you can see, the PSD curves of all the mixtures fall within the upper and lower limit of a capping layer that is set by the Australian Rail Track Corporation. We used 3 confining pressures for the static triaxial tests in this study. And these confining pressures were based on the range of confining pressure that is usually observed in practice at the level of a capping layer. So when we move, now we move to the experimental results. When we examine the stress strain curve, the first thing we notice is that all mixtures experience a post-peak softening behavior, and that the peak stress decreases as rubber is added to the mixture. This is due to the lower shear strength of rubber particles. So rubber particles have a lower shear strength than coal wash particles, and this is why we can see that there's a reduction in the peak deviator stress as rubber content increases in the mixture. On the other hand, we can see that the ductility of the material is significantly improved when we add rubber to the mixture. And this means that we can avoid sudden and catastrophic failures if, for a certain reason, the live loads in practice surpass the strength of the material. You can also notice from these figures that the characteristic state and the critical state for all four mixtures is almost the same for rubber contents that are between 0 and 15%. So for relatively low rubber contents, we can conclude that the addition of rubber does not actually affect the characteristic state or the critical state. It only affects the peak state in static triaxial tests. And these results were also shown in previous studies where the rubber content was less than 40% in the mixture. The initial tangent modulus is another indication of the ductility of the material. And if we look at this graph, you can see that the initial tangent modulus decreases with increasing rubber content, while the rate of this reduction decreases when the amount of rubber increases. So the greatest reduction is at lower rubber contents, and as the rubber content increases, the rate at which the initial tangent modulus changes with rubber content decreases. Again, this indicates that rubber improves the ductility of the material, which also implies that we might have higher axial strains for the same stress level. If we look at the peak friction angle, we can see that the mixtures have a peak friction angle greater than 45 degrees for confining pressures that are less than 50 kPa. 45 degrees is the peak friction angle that is recommended for the sub-layers in transportation infrastructures that are not the main bearing layers, like the sub-bays in roads or the capping material in railways. So 45 degrees is considered an acceptable peak friction angle. And you can see that for the range of confining pressures that are usually encountered in practice, which is around 40 kPa, the peak friction angle of all the mixtures is within the acceptable limit. Finally, the void ratio in this picture is plotted, but here we used a modified void ratio because we cannot account in static triaxial tests, we cannot actually monitor or account for the change in the volume of the rubber crumbs. So rubber crumbs are deformable and compressible when they are confined. And because we cannot actually capture this change in the volume of the rubber crumbs, we defined a modified void ratio, which is the volume of voids over the volume of coal wash. And because it is easy to monitor the volume of voids in saturated static triaxial tests, and the volume of coal wash can be calculated from the initial void ratio. So we can monitor the change in the modified void ratio of the mixtures. So we can see that the modified void ratio at the characteristic state, which is plotted in this graph, is higher when rubber is added. So it increases with increasing rubber content. This indicates that the addition of rubber facilitates the rearrangement of particles in the compression range, and it results in a smaller volume of voids, which is attributed to the deformation of rubber particles that provide a more compact packing of coal wash particles when the mixture is subjected to loading. So for the same rubber content, we can see that there's a slight reduction in the modified void ratio with confining pressure because the range of confining pressures that was used in this study was narrow. So we don't see a significant change in the modified void ratio with confining pressures. And finally, if you look at the breakage index and the saturated hydraulic conductivity of the mixtures, we can see that the breakage index decreases with increasing rubber content. And this was the main reason why we added rubber content to the mixture. We added rubber in order to minimize the breakage of coal wash. And indeed, we can see that there's a significant reduction in the breakage index as the rubber content in the mixture increases, although we employed a higher compaction energy to compact the mixture with higher rubber contents. So even though we used a higher compaction energy, we still observed a reduction in the breakage index as the rubber content increased in the mix. As for the hydraulic conductivity, we can see that the hydraulic conductivity of the mixture increases with increasing rubber content, but it is still within acceptable limits for a capping material in railways. And the hydraulic conductivity can actually be predicted using this equation, where A, B, and C are constants, and RC is the rubber content in the mixture. And we can see that there's a good agreement between the measured values and the predicted values. And finally, this figure shows the maximum work dissipated by the CWRC mixture, the mixture of coal wash and rubber crumbs, up to the point of failure, as a representation of the maximum energy that can actually be absorbed by the material during loading up to the failure point. As expected, the energy absorption capacity of the mixture increases with increasing rubber content because rubber is energy absorbing. However, this is more evident at higher confining pressures because the compressibility of rubber is more evident and it increases with the increasing confining pressure. So based on these results, a 10% rubber content was suggested as the optimum rubber content. These preliminary results or preliminary tests showed promising results and that the proposed mixture of coal wash and rubber crumbs can be adequate for a capping subballast layer in railways. Further cyclic triaxial tests were also done to further verify that this mixture can be used as a capping material in railways. And the findings of these tests are now published in Q1 journals. I will share with you in a moment a list of some of these publications if you want to know more about the findings of this study. So this is a list of peer-reviewed publications that are related to this research study if you wish to know more about the latest findings. And finally, I would like to acknowledge the financial assistance that is provided by the Australian Research Council. Also, the support and guidance of my supervisors is gratefully acknowledged. And finally, the support of the industry partners and the technical staff at UOW for their help in conducting all the tests in this research study. Thank you very much for your attention and for your time, and I'm happy to answer any questions you have after the presentation.